Any question, please drop me an email. I'm happy to help you. I believe everyone knows my email address. You can drop an email and tell. In case if you want, I will share my email address. Right. So this is my email address. So you can use that email for ask any question related to the subject and stuff. And there is a one called GHH, a student name there. I'm going to remove you because I don't know who you are. If you are giving your email address, sorry, your S number or your name, then I can rename. Unless I could remove you within next couple of minutes if you are unable to share your details, because I don't want any anonymous people in here. So please share your details. GHH someone, and I'm not letting these people to inside this class. It might be a problem because we don't know who you are, right? It's a security threat, right? You can share the details with me unless you will get removed from the meeting. I'm really sorry for that. The reason behind is I don't know who is that, right? Simply you can tell your name, right? All right. So we'll start our discussion. There's a question to discuss the question. The cat questions. We'll see. First of all, we'll go through the materials because that's the main task. Uh, then, if time permits, we'll go to and we'll have a discussion with these questions and how to answer these kinds of questions and how to get the best among these questions. So, bit of recap. I got one request to discuss quickly with this unsupervised learning. What is this unsupervised means? Right. Once it comes to this supervised and unsupervised learning, the basic, the most essential is actually this labeled data. Right. We have labeled data. That means the labels are given. For an example, these are circles, these are squares. So if we take the supervised learning, we have all the column details, like if it is in a tabular format or it's in a table kind of thing. For an example, if it is in a Excel table, Excel or Excel, Microsoft Excel document, we can find the column names here, age and stuff. Here we don't have labels in here, right? For an example, this is something x1, x2, x3. So we don't know. The names are not given. So that's the main difference in between supervised and unsupervised learning. And if we take a bit more, right? Now we can see this unsupervised learning is mainly focusing on clustering and association. Now, supervised learning, since we have the columns and other related data, it's much convenient us to do many things because we know what is exactly in this case. We don't want, actually, the problem is we don't want, right? We don't want to take this kind of things specifically for clustering, right? For cluster a person, we don't want, right? We don't want a clustered person in the given scenario, right? So that's why we are using unsupervised learning. For an example, if you want to take similarities among something, right? We don't want anything, right? It might be color, it might be shape, anything. X, we tell simply it's X, right? Based on X similarities, there might be a range. For an example, 0.5 to 0.8. We can cluster. But we don't know what is this 0.5 means. It might be pH value, it might be phosphorus value, it might be nitrogen value, it might be anything at the end of the day. We already know a range we have, and based on that range, we are clustering. The other main problem is association. Association means combining the values or similar based on similarities. We are finding different kinds of similar patterns or similar uh, clusters, right? Similar structures among a given set of data. So those are the main problems that we focus under this problem, right? So the unsupervised learning focus for that. And if we take in a very high level overview, you can see the supervised learning, unsupervised learning, and how these things work. Supervised learning with the discrete data, we are mainly focusing on classification. Discrete data with unsupervised learning, we are focusing on clustering. Supervised learning with continuous data are going for regression, and unsupervised learning with continuous data, we are going for dimensional reduction. So altogether, you should initially think this is one of basic and very simple discussion. You should initially think what is the problem that I'm going to solve, whether it's a classification problem or a clustering problem or a regression problem or a dimensional reduction problem, and so on and so forth. We have problems in this case. We are uh, getting into these problems, and based on the data availability, we are solving something. It's not just a prediction, it might be something else too. Like for example, we can have a regression line. We are regression something, or else it might be a simple binary classification. We are dividing into two parts. Something could be happen at the end of the day. That's the story. I believe you got some high level story, guys. To be honest, you need to spend a bit of time, then you can understand all of these things, right? Any questions quickly before moving towards to the today discussion? uh, for the cat paper question 3, I think that's R code actually. Uh, it's something that you can discuss with Kirushika. For the question 2, because I think it's good to give some information. Q2 mainly focus on what is that, accuracy. uh, Accuracy 100 out of 100 means there is some problem, right? Accuracy 100 out of 100 means, because I'm getting continuous chats to discuss, so that's why I'm telling, right? Accuracy 100 out of 100 means it's overfitted, right? So it's something weird, so it's not acceptable. There might be some reasons: insufficient data, color, class imbalance, and something. So at the end of the day, if someone is telling my model is performing 100 out of 100, it's false. If there's no possibility to have 100 out of 100 accurate results you can find, then it's a problem. So you can't have that kind of thing. I believe that is enough. A small overview is enough, right? If you have any questions, you can definitely drop an email, then I would elaborate a bit more, then fine. Right. Next, we'll go to the data cleaning part. Actually, this is something very important once it comes to the data scientist's work. So you should have a clean data set. Once you received your data set, you should convert into a clean data set, a purified data set, because as you already learned last time, garbage in, garbage out. So if we train, or if we teach someone incorrect things, then the response is incorrect. So that's the garbage in, garbage out concept. So to avoid this story, what we are going to do is we are using data cleaning or data cleansing. Sometimes you can find in different places. Data cleansing or data cleaning is going on there. So a bit of introduction. Data cleaning involves identifying and correcting errors, inconsistencies, missing values, and other issues in the data. So what happens in this case, we are having very dirty set of data. Initially, we have a dirty set of data, Now what we are going to do is we are going to transform that data into clean data set or a purified data set. For the purification, we have to perform different kinds of actions similar to the water purification process thing, right? We have to transform the unpurified data into purified data, clean data, because we want to find where the errors are, or sometimes, for an example, a numeric column might have a string character, or some of inconsistencies might be there. For an example, uh, the range of a given column, right? The range of a given column is, now here we have a column over here, then this value something like price or something there, 100, 200, 500, 800, or likewise we have. Eventually we have 2 million in here, right? And again 100, 200 and something. These are something weird, right? Something weird, some inconsistent data makes our data into the inconsistent stage, and sometimes missing values are missing, and so we have to identify these kinds of issues in a data set prior to the analysis. That's the whole discussion related to this data cleaning. Primary purpose is to improve the quality and the reliability, because unreliable data set means we can't do anything. And if we don't have a very high quality data set, at the end of the day, it's a big problem, because it's a must to have a clear, high quality data set. Then we are feeding that high quality data set to the model. Then the model will process that data. The model will tell, all right, this kind of perfect accuracy, a perfect output at the end of the day. This space is actually really essential to get proper decision making process, because if something gone wrong, the rest of the things are gone wrong. So we have to spend a lot of time to clean this data set. Now usually the rule that behind this data cleansing or the entire process is, for data cleansing EDA part, initially data extraction, cleaning, and EDA part, we take 80% of time from the entire data science project. So rest of the 20% of time is required to model development and performance testing. Now you can see the importance of this data cleaning and cleansing and the EDA parts, right? Because we want to get clear understanding how the distribution of the data is. So what are the steps? We can go for data auditing. This involves examining the data to identify potential issues such as missing values, duplicates, outliers, inconsistencies, and formatting errors. A lot of things might be happen, right? We are going to examine what are the potential issues in a data set. Some of common things are discussed in here. Missing values. Some of the values are missing values in the sense, we have a data set here, right? This is my data set. We have a data set here and data is in here. Finally, someplace some of data missing, right? Some of the data is missing. This place no data at all, and this place no data at all, and this place no data at all, and so on and so forth. So such kind of things might be happen. So what happens at the end of the day, the inconsistency is incurring a lot, because we don't have proper data in here. My general suggestion is, like, for an example, think we have some missing data, then how to handle these things, right? We can remove the data. We'll discuss all of these. We can remove that column as it is. For an example, 90% of data is missing in this column. Data 90% missing. So we can't do anything at all, right? Because we have 10% that then at the end of the day, if we use that column, then it's a big problem. What happens for us is we have to consider what kind of thing that to do. 90% missing, delete. There are a couple of things. Case 2, I'm discussing case 2. Something is missing, right? 1%, 0.5% is missing. So we have some imputation methods. I'll discuss these things later on. We can fill the data. We can add some data. Some of the methods like fill using mean value or the mod. Different imputation methods we have to fill the data. And sometimes there might be some duplicates in a given column. What happens in a given scenario? If we have duplicates, we have to remove the duplicates. For an example, we have a set data set here, right? A data set here, and this column and this column and this column. Sorry, this row and this row and this row. All of these details, not one. The column 1, column 2, and column 3. If we consider column 1, column 2, column 3 is equals to column 1 and column 2 and column 3 equals to this one also. So all three rows representing extract same data, isn't it? It's representing extract same data. Now what we need to do is we need to delete these two and we need to keep this data unless it might be a problem. Right? So these are the things that you should understand whenever we are doing this kind of auditing. Outliers, I discussed last week also. Outlier means if we plotted over a data set here, then we can find some data is here, right? Somewhere here, somewhere here, somewhere here. All of three values points are actually outliers. It's out of our scope. Right? Some formatting errors, inconsistencies might be there. So you should audit the data set prior to model development. It's a must. Now, probably for your final CATs or something, final assessments or whatever things, you might have to develop a model or train a model. To train a model, if you are taking the raw data set and if you are just fit the data set and if you are going to predict something, then your marks will affect a lot from your assignment wise, because initially you should have a thorough EDA part and a cleansing part. So these are very important to do in data science and AI context. If it is joined to the industry and if you are using a raw data set and if you are doing a model development, your predictions are inaccurate. So the business decisions are inaccurate. At the end of the day, business is going down. So you might be the culprit at the end of the day, and you might face a lot of issues. So this EDA part and cleansing part is really important. Again, I'm telling. Let's discuss further steps. We can go for data corrections. Now we are going to fix in some of issues. For an example, typos. Simple typos might be there. Sometimes simple spelling errors. So we can fix those things. We have usual natural language processing kind of things to fixing these typos and stuff. Yes, of course. And if it is like some decimal values and stuff, we can fix all of these things. Yes, of course. But general suggestion is actually to go for a manual review too. If you have some issues, though you have a very large data set, then we can go for a manual review. Sometimes you might you can't think that can do manually, right? So if you have 1 billion data set, the thing going for a manual review is really hard, right? But it's happening, guys. For an example, in Sri Lanka, I know two companies. They are the job that they are doing. The people who are doing there is manual review. There are some inconsistent data is coming for them. Then they manually edit the data. That's their job, right? So it's kind of a weird job actually, but that kind of things also happen in this data science aspect. So fixing typos or finding some common issues, say very simple issues, right? We can fix those things. That's why we are telling data correction. We are correcting the data. Standardization, the format of the data. Now we have a data set. It's not standardized. So what we need to do is we need to standardize. Sometimes we want to scale it, right? Now, sometimes if we take the log values of a given data set, we might shrink the data set, right? We can go for different kinds of techniques to standardize the format of the data. Sometimes unit conversion might be support for you. right? Sometimes unique conversions might be support free. Then filling in missing values. These are using usually for the data correction. As I told you, if we have some missing values, we can fill the missing values. We can impute the data. We can fill the data. Imputation means we fill in the data. We are getting the mode or mean of the data column. Now, for an example, assume a data set we have, age is in here, right? And if we take 18, 18, 18, 18, 18, 18, one missing value, 18, 18, 18, 18, 18, 18, 18, missing value, 18, 18, 18. What could be the missing value? If I ask from you, your answer is definitely 18, right? The reason behind, as per the distribution of this data, we can clearly state, yes, it should be 18 because it's nicely aligned to specific one, right? Specific value. Or it might be kind of a small range, 18, 18, 18, 19, 18, 19, 18, 19, 19, 19, 19, missing value, 18, 19, 19, 19, 19, 18, 20, one might be there. Then the probability of getting 18, 19, 20 might be extremely high for this missing value, right? So that's what we are telling the imputation. We can fill the data, but the distribution, first of all, to get this idea, you should see the distribution. If the data is highly skewed or somewhere like gone here, like this kind of a distribution of the data, once you visualize, you can't impute as it is. Now, if you have a data set like specifically all the data, age, right? Age, the first one, second, and third, and all of these people are like in the same place, all the plotted over here, then you can simply say what you need to understand is whether I'm going for a mod or a mean or the whatever the value, it should be a valid with a valid reason, because we are filling a data, and at the end of the day sometimes it might be a risky scenario. Now this person is not age 18 at all, sometimes it's a 30, age 30. That's why this person purposefully skip filling the data, right? So it could be an outlier and it could be a big problem at the end of the day by fitting this kind of a data, right? Actual age, if we go back and forth and research again, and we found this person's actual age is 30. Now this person is worried to give the age 30. That's why the data is missing. As a data scientist, you fill the data as 18. Now again, it's a problem, right? That's why you should be clearly get an idea prior to this filling this data. It's risk. It's a really, really high risk, because if you don't know the data and you are filling something, means you are taking a risk over the problem. Right? So you should be very careful in this kind of a scenario. Right. Next, we'll see a bit of these things. Then data transformation. This involves with transforming data into format that is suitable for analysis by applying techniques such as feature scaling, normalization, encoding categorical variables, reducing dimensionalities, and so on and so forth. Today, we are focusing on this data transformation a bit more under this feature engineering. So you can learn a bit more. Basically, if we just give very high level overview, feature scaling means like transforming the data into a specific scale to get an idea. Normalization means transforming data into a standard range. And if we take encoding categorical variables, then it could be something like changing the data. For an example, male, female is converted into ones and zeros. Sorry. Then reducing the dimensionalities means we have large set of feature set, but that features are not much important, some of the things, so we can reduce the features that not related, some of the features missing, so we can remove. So many things might be there at the end of the day. So we'll discuss it a bit of further things in later of today. Data integration. This involves combining data from multiple sources to create single data set, which may involve resolving differences in names, formats, units, and measurements, and so on and so forth. Data integration is a very complicated point in our data science life, because we are taking two data sources and we are going to combine. Most simple and something that if I ask without a zero, like you don't have any experience, but you can still say, right, we have two tables in here. What is the most basic requirement to be same to be to combine these two into one table or merge these two tables? We have one, two, three, four, right? We have four features over here. One, two, three, four. Extract same four features should be in here. Extract same four features should be here. I'm emphasizing it. If not, we can't merge as it is. Sometimes if we have five, then sometimes we can take one, two, three, four here and combine to the fifth one. What is the biggest problem happens in this case is, in this set of data, for an example, think we have 1K data here. This 1K data, the feature 5 is completely empty, isn't it? It's completely empty. So these kinds of issues might be occur in real world scenario too. So you have to deal all of these things. Think how to handle this kind of a scenario, merging, combining, concatenating, right? Concatenating is very easy, but merging is a bit hard. So the similarities of the values, and sometimes one column, we have two tables over there, right? Here we have in our database, we have two tables. One is in kilograms, same measurement, weight, right? Kilograms. The second table we have grams. There might be a situation like this. So though it's weight, the values are different. At the end of the day, we are in a big trouble. So what we need to do is we need to transform the data initially, neither way, whether kilograms to grams or grams to kilograms. You can convert according to the problem that we have. If the problem is going for a very serious in the weight, then the option is going for kilograms to grams. If we don't bother a lot, then we can go for grams to kilograms. We can go back and forth because both are same, but decimal values might be there, some of precisions might be having some issues, and so on and so forth, right? So think what kind of scenarios might be happen at the end of the day. That's why we are telling units and measurements and the variable names, formats, many things might be, right? Many things might be there at the end of the day. Next, data verification. This involves verifying that the data has been cleaned and transformed correctly, and that there are no remaining errors or inconsistencies. We are verifying the data. Similarly, the verification and validation process that you learn under this software testing or performance modeling or somewhere, I don't know where you learn. So somewhere you learn at the end of the day. Now the objective in this case is verify the data is clean and we can use it. There's nice distribution. I'm not telling it the standard bell curve distribution. There might be some skews too. That's fine, right? Transformation is happen somehow, and it's clean and transform, and somehow the data set is nicely aligned. There might be minor issues, right? There might be because we can't take fully clean data set. If we have very clean data set, then people will do everything for us. That's not a big deal. The biggest deal that we need to do is extracting data, merging from different sources, cleansing, EDA. So those are the complicated things as it comes to this data science context, not model development. For the model development, it's a couple of lines. If you want KNN, K-means or whatever, it's a couple of lines. If you know the process, that's it, right? Even ChatGPT can help us to complete all of these things, to be honest. If you ask, I have this kind of a data set, a clean data set, then ChatGPT will generate all the code for you. You can copy paste and you can visualize and do everything at all. Right? So nothing, no problems at all. The problem comes, we ask from ChatGPT, I have this kind of data. Can you clean the data? Then if you have 1 million data pasted over there, then it's into a big problem. But very soon they'll have all of these things, but yet we don't have, right? That's why I'm telling this data cleaning and ED and getting decisions in this place is the complicated point than any other thing, right? So these are some of basic steps that you can follow. So go through one by one, clear, audit the data, correct the data, transform the data if required, then integrate from different sources. And I can't say this is the very first, this is the second, third, and so. So it depends. Sometimes initially you should integrate the data. Number one should be integrating data. You have multiple data sets here, right? You have multiple data sets here. This is your step one, right? This is your step one. This is your step one. This might be something a bit weird for another project. This is your step one in here, in this scenario. That's what I'm telling you. It's all about how, it's all about the problem. It's all about the problem and the solution, what you want to do, what you want to actually come and tell. There's no hard and fast rule to go for integration, then go for auditing, then go for transformation, then go for correction, and so on and so forth. But general processes we have, right? We once the problem throws to your head, you have to think, you have to get the decision. What is the most optimal path that I need to carry out? These are some of example steps that I have given, but there might be much more complicated and most important or aligned to the problem might be there. So you should think all of these things very well. Some of techniques here, removing duplicates. This involves identifying removing rows that contain duplicate. We remove the duplicates. That's the very first, the most simplest technique in this case. Remove the duplicates, students, whenever you got a data set. From my point of view, what I'm doing, I'm finding any duplicates are there, then I'll delete that duplicates as it is from there. Number one, that's the number one, because with duplicates, whatever things that we are doing is a problem. So your very first thing is read the file, next find the duplicates, delete the duplicates before you doing anything. That's very important. Then handling missing values. This involves identifying the missing value, missing data, either removing rows or filling the values, such as mean imputation, median imputation, or interpolation. So you can go for a technique and you can fill. As I told initially last couple of minutes, I told the same story. There could be a risky scenario that once you are filling or performing this interview, imputation or interpolation, these are just some technical terms, but the story is same. Imputation means filling with the mean value. Some big term is there, that's all. But you are at risk if you are filling more than 25% of the data. So if you have empty spaces or missing data more than 25% in a given column, please don't fill the data. It's a risk. My general suggestion is take it somewhere else. Then do the analysis for the clear existing data set. Then you can have a clear data set rather than filling lot of data. So that's something that you are getting into risk. If you want to get the risk and see and play and get, that's fine. But general suggestion is, my suggestion is, don't go for imputation or interpolation if we have missing values more than 25%. It's a risk. You can, right? I'm not telling not, you can, but it's a risk. Sometimes the risk might be extremely high. Then removing outliers. Removing outliers means once you analyze the data set, you can find one person is extremely different. I'll explain it again because these are very common terms, but we should know these are buzzwords in our DS context, the data science context. Here, what we have here, like the data set is here and one is here. I think we have given a cat paper for you. All the students got around 25, 30, 35, 20, 20, 19, 18, 0, 0, 0, 0, 5, 10, 0, 2, 5, 8, 12, 30. Maximum is like that. All of a sudden there's a student 95, right? We have 217 students in our data science class. Among the 217, 216 here, one is here. Something gone wrong, right? Something gone wrong. So this is an outlier. This is something that gone out of the scope, and that is something that we have to consider. Right? Very simplest suggestion from many data scientists is remove that data. Right? Remove that data as it is, then take the rest of the data for your work. Yes, of course, it's agreed because something gone wrong over there, then fine. But I'm doing some of data science work. We are getting these outliers in business world, guys, to be honest. Like customers, especially, we have this customer data. It might be like this, right? Most of the people, for an example, I'm changing the story for you to understand. Most of the people around the purchasing items, 5,000 to 10,000. Assume, right? The data is like here, right? 5,000 to 10,000 and stuff. And there is a person who purchases all of a sudden 100,000 items a given day. If we delete this one, we losing a premium customer, right? A valuable customer from our data set. Sometimes lot of people, 90 percentage, 30 percentage, whatever the percentage, people might be under 1,000. This person is extremely valuable person for our business, right? So removing that valuable person is extremely a big problem at the end of the day, right? We have to entertain these people than this person, these people, right? Because these people generates a business for us, yes, of course. These people helps us, yes, of course, no issues at all. But profitability wise, this person is extremely high, a valuable resource for our scenario. So removing outliers, again, you have to think twice. Don't delete as it is. I have come across many places. People just deleted as it is. My general suggestion is take these outliers separately and analyze their data in a separate forum. That makes sense. Then you can combine and see finally the big picture. You can get, there might be some different people who are purchasing very high. All of a sudden, once in a month, sometimes these people visiting only once in a month and purchasing everything for the month and they left. These people, the daily routine. So if you want to give a promotion, you can give a nice promotion for these people too, right? Because we know 25th or 26th, they will come and they are purchasing this. And what we are going to do now, we are going to give a 10 percentage discount if your bill is above 125, because we know 100,000 they are purchasing, the purchasing power is 100,000. We are going for 125,000 and we are going to give a discount for them, a decent discount. Definitely they'll go. Definitely they'll go, guys. That's the point of a data scientist work. It's very interesting, right? We are getting people into our business, and we are getting the people into our business means we are getting more profit, and it's our brand. So don't delete outliers, though everyone is telling. If you're vigilant, if you're wise, if you think clearly, if you sacrifice a bit of time, definitely you will find very important values from these outliers. Sometimes this outliers an incorrect data. That is very common scenario, right? Someone entered some incorrect data and left. Or there might be some system crash. There could be a situation like that. There can be a situation like that. So it's very important to understand this outlier handling. So you should be very careful whenever you got an opportunity to deal with outliers. Standardizing data is very easy. It's coming to a very common format or a scale. We have different kinds of scaling methods. We'll do some of the things later on. Very simplest method is going for log transformation, box transformation, right? Very basic methods we have for the standardization data. Sometimes we have formatting like or scale changing, for example, kilograms to grams kind of change. All of these things are like changing the data into some specific place or specific value. Encoding categorical variables, we want to convert numerical values to convert to numerical values to use the machine learning algorithms. So we have to encoding these categorical variables. I'll discuss in under this speech engineering today, like for an example, one hot encoding and so on and so forth to get to transform this data. So the real scenarios are very minimal with this encoding of these things, because we are facing some issues, real world scenarios, right? Theoretically, yes, of course, we can convert and we can do all of these things, but practical scenarios, in the practical environment, converting to categoricals like minimal. If you take overall data science work, it's around 10 to 5 to 10 percentage of time. But missing value handling, imputations, outlier detections, standardizing, those are like 95, 98 percentage of time we are day-to-day using. Some of the techniques that I discussed, that we use to clean the data, then we standardize the data, then we get the data into a proper place, right? So that's the objective, and this is the places or the activities that we are doing in this scenario. Right. I know it's a very high level discussion go through, but I'm really sorry, guys. This is very tight 2 hours discussion. Unless it could be like a nice discussion with examples and coding practices and all of these things. But with the time limitations, I'm going to have the essential theories with you. You go to YouTube or ChatGPT or somewhere and see whatever that we discuss in this class, and get some hands-on experience. Go to Kaggle, you can find courses over there, you can go to competitions over there, then check what you can do, right? Simply you can go for logistic regression, find the logistic regression related data sets and experience all of these things. For there are some courses also there. Give a try, see what are these things, get much hands-on experience, then only you know the whole story, not the theory, right? I'm not much of theoretical person, though I'm discussing all these theories, because if I go to practicals, it takes time, right? It might be really hard to tell all of these things. That's why I'm going for the essential theories. You go for anywhere, I'm really open. You can use any tool that existing in the world. You give a try, see, learn, right? See and learn, not just what happens theoretically, practically see how these distributions are, then you will get the experience. Oh my god, it's interesting, right? Yes, time for quick Q&A related to the discussion. Yes, there's a question. In that case, those data will be removed from dataset. Sorry, I missed the chat. Uh, could you please elaborate this question a bit more? Then I can explain. There is another question. If we have some time, can we go to small real world example of data processing sometime? Probably real world scenarios in the sense practical, if I'm not mistaken. I don't think so within this time I can, but sooner or later I'm planning to have this H5P kind of things to be added. We'll see, because I'm just coming to the context of this open and distance learning, so it's moving towards to that place. I have done remote teaching, but the stories here is a bit of different, because the schedules and examinations and bit of the difference with the national universities we have. So I'm adapting to all of these things, and I don't have access to the videos. I'll share the video. Yes, I'll share the video. I have shared with Kirushika to upload it. I don't have that access to that drive location. Somehow, if you want, I can share the data day two school with you. I can upload to YouTube and I can share. Then you can download from there probably, right? Yes, I can upload it and I can share with you the link. Then you can download from there. Standardization data means, for an example, the question is, can you give us example for standardizing data? Standardizing data means, for an example, think we have a data set like this, right? We have, I'll show you. Uh, Yes, right. Now, for an example, think we have a data set like, here's the page, right? We have a data set like this, guys, right? So this is my graph, and the distribution is like this. And here it's 1 million, right? Here it's starting from 100,000, right? The data is 100,000 to 1 million. So the range is extremely high, right? So the data is plotted over like this, very, very, very large range. So what we can do, simplest ways, we can get the log values of each and every, right? We can get the log values of each and every. Then we have another graph. That graph is very simple. Right? Similar story. We transform, we get the log value of each and every data point. These are the data points that plotted in here. Each data point transformed to uh, the log value of each. Then we have a small value. These small values might be fit for our case because it's very easy to interpret because the range is minimal. Now, if you know the story, right? If we take the log value from 100 to 1 million, it's a very small range. It's not going for 1 million of a range, or 100,000 to 1 million. The range is different. So this is a very simple thing that you can do. Then you can go for box transformation. It's another transformation. There are standard scaling methods. This data science context is extremely large, guys. Right? It's like an ocean. So you need to dive and dive and dive, spend hours and hours and hours and hours to understand the whole context. It's extremely large. Right? And I can't tell this is the perfect solution for this. We can give, it's all about our experience. My suggestion is, that's why I'm doing, go to Kaggle. That's the best place, if I'm not mistaken, to start learning, because already some codes are existing by the great people developed some codes in any practices or competitions and stuff. Real world data scientists are involving in there. Go to Kaggle and create an account, see what happens in there, get that experience. That makes sense rather than learning all of this theory. The learning theory is essential because you should know theoretically what happens, outliers, what is this outlier and how to handle this outlier, what happens if we remove an outlier, what happens if we keep an outlier, and so on and so forth. Practical exposure is really important to get the real taste, unless you just get some theoretical exposure only. Any other questions? Right, I will share the slides also. Probably we'll see everything to sort out Monday. Meanwhile, yes, I can give me a couple of minutes. Sometimes I have already uploaded, not sure. Somehow I'll share the link with you today itself. For the week, this lesson also, I will share earliest as possible. Then you can go through whatever things. Right. I assume all good. Sometimes bit of complicated. Give a try, see what's going on. Right. Next, we'll go to feature engineering, dimension reduction, PCA, and SPD. These are some techniques that we are using. Feature engineering and dimension reduction, model selection, evaluation, and regularization. I'm not going to discuss much of the probability methods and logistic regression. Clustering and hierarchical clustering, I'm not discussing in detail, but I will give very high level discussion today. And I'm planning to complete those things in day school 4, right? Because it's something that we have to take in a separate forum, unless you might be confused. So I'm mainly focusing the rest of the things to discuss feature engineering and dimensional reduction. Feature engineering is the process of creating new features from existing ones or transforming the existing features to improve the performance of machine learning models. Now, feature engineering is a big process at the end of the day, because entire data science story, entire data science world is going towards this feature engineering. Because if we do not perform well with these features, at the end of the day, what could be happen? We might into a trouble because we are unable to get a proper work done. The reason behind is we don't have proper idea with what kind of features that we have, right? We don't have much idea what kind of features that we have. Features, again, I'm telling, features means this kind of, if you take a table, right? If you take a table, this kind of things, this is a feature 1, feature 2, feature 3, feature 4, feature 5, and so on and so forth. We develop these models based on these features. If we take a real world scenario, yes, of course, if we take a real world scenario, we have a face detection system. Key features: where your eyes are, nose is, mouth is, chins, forehead, right? And those things are the features that we can consider. Right? The size of eyes, color of eyes, shape of eye, nose, alignments, right? Different kinds of things might be there. All of these are features. And some of features might be having some issues. So what we need to do is we need to get a clear overview to perform this feature engineering. Number one is the problem. What is the problem that we are going to solve? For an example, again, I'll get the same scenario. We have a face detection system, and objective is to detecting face. We need to create uh, features. We need to focus on features based on the problem. In this scenario, we have to get the face related data. And if the problem is not the face detection, but the problem is changed to mask detection. Now, now the story is different. Now the features are different, because now we want to see the mask detection. Now we can't see the mouth and the nose, most probably. People covered it. So features are different now. Got it? Now the features are different. Now we can find these features might be there, plus some of the features removed, plus some of the features added. What are the removed features? We removed mouth sometimes, because mouth is hidden. We can't see. Sometimes nose is covered. Sometimes. Right? Some of the time part of the nose is removed. So those kinds of scenarios might be happen, might be occurred, right? Might be in real world case. So that's another problem. But same phase, same phase. I'll take another problem. Now our problem is not face detection, not mask detection. Now we want to do a helmet detection, whether a person is wearing a helmet or not. Same face features, but for a different problem with different aspect. Now the features are different. Now the features are different. So you need to transform sometimes the data. Sometimes you need to collect some data from different sources. Sometimes you have to do different kinds of analysis at the end of the day. Eventually, all of these things are very complicated, because one feature might affect a lot. Sometimes you miss that feature. Sometimes you added 50 features, but actually we need only 3 features out of 50. We can remove the rest of the 47 features as it is, because those are not affecting a lot for our model. All of these things can discuss under this feature engineering for. This feature engineering is a very important aspect at the end of the day. Similar to the data extraction, simulative data combinations or data merging, data cleansing, very important. EDA, very important. Now I'm telling feature engineering also extremely important. So before you perform a model development, you should, it's a must to go for this feature engineering, a thorough feature engineering. And you should tell, yes, I kept the most essential features, and these are the most important features under this scale for perform this action. That's your final term, right? After clear feature engineering, what you can tell is, I have taken this data set. Sometimes it might be clean data set. Yes, of course, most probably it's well clean data set, right? It's most well clean data set. But some of the features in that data set is inappropriate. Some of the features needs to convert into another type, right? So this discussion is going under this feature engineering for. I believe you got a clear understanding what is this feature engineering, because EDA and other stuff is quite popular. Everyone is discussing, right? Everyone is discussing what is EDA and all of these things. But this context is a bit of a complicated story. It's a bit of complicated point. So you should go through features now, not the data in here, but the structure, right? Data in the sense here, the data here we have, right? These are the data we have, like uh, age 25 to 35 or something, names and plus. But in this case, we are focusing mainly with these columns. Now, once it comes to these columns, definitely it's tightly coupled with the data available for that. Right? Our objective is to get most appropriate features, most accurate features, most essential features, most powerful features for our model at the end of the day. Then only we can go for a nice, clear implementation. Then we can do a nice predictive analytic or whatever, right? Whatever the analytical work that you want to do, you can do. I believe that is very clear for you. We'll go for some of techniques here. One-hot encoding. One-hot encoding is convert the categorical variables into binary matrix representation. Each category becomes a new binary feature, where one indicates the presence of category and zero is absence. Whether we have data or missing the data. Whether we have data or we have something missing. So those things that we are going to discuss in this case, right? So it's very important to understand how we are going to discuss, or we are going to work, right? We have categorical data. Categories means we don't have a specific line at all, very clear, right? We have gender, right? Male, female. Those are categorical variables. Now, these categorical variables convert into a binary representation, 1 or 0. If I ask this question, I'll draw it to make your life much easier. We have a column here, gender. Male, female, 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 male, female, male, male, female, male, female, male. Now what we are going to do is we are going to convert that value here, right, to 1 or 0. Right? Now, new binary feature. What is the new binary feature we are involving with? Male means 1, female means 0. Male means 1, 0, 1, 0, 1, 0, 1, 0, 1, 1, 0, 1, 0, 1. Right? Yes, of course, it's a perfect story to do. But the problem, guys, now computer has no idea to tell, right? Computer is just a dumb device. There's no brain at all. Now, if we ask, uh, can you give the mode or the median or the values, then it will generate, yes, of course, for gender. The gender would be 0.8, gender would be 0.6, 0.5, 0.2. Problems, right? Extremely a big problem, because Now, once we assign a value, that means it converted into a specific range 0 to 1. So mathematically, there should be a person with 0.6, 0.2, 0.8, and so on and so forth. This, of course, sometimes practical scenarios, there might be some males like females, females like males. So we can categorize into 0 point some values. Yes, of course, yes, that's fine, right? But I'm speaking. Generally we can't, right? There might be a person, a male or a female, right, or something, I don't know, some different kinds of cases might be there. Then you can apply to different categories in these cases, right? So those are the points that we should understand, right, right. So it's important to understand, to conversion this process would starts a big problem, a set of problems again, clear? Because by converting categories, we are giving a value in the sense we convert it into a sequence of values. So there might be a person with 0.42, 0.4, 0.45, or 0.1.11.111. Very complicated. So one hot encoding is very important, but you should handle those things separately, right? You should handle separately, right? Why I'm emphasizing all of these things? Some people just transform it to using one hot encoding and see the story. And after the evaluation, I can see, oh my God, there are some issues in this case because of this one hot encoding. Then feature scaling. It ensures that all features have same scale, preventing certain features from dominating due to larger magnitude. Common scaling techniques include min-max scaling, z-score normalization, and stuff. Now, I believe everyone experienced this pain of this z-score, right? So what happens, this normalization, z-score normalization, we are taking average people as 0, then we distribute. You are above the average or you are below the average, right? There are some arguments, of course, there's no arguments at all. There are some biasnesses in this case once it comes to the A level Z score, because I know personally there are a couple of people completed their examination in Polonnaruwa, but they came to Nugegoda to do the lessons and learn their group classes, and all of these things happen in Colombo. Then they back to Polonnaruwa and done the examination, then went to engineering faculty, right? Those kind of examples that I have in my life, yes, of course. So it's not representing the area that you are living, yes, of course, right? The story is to but objective of this z score is to normalize, to come to a standard scale, right? To see the distribution in a given data set. Highest is always 0, then we divide into 2 from -0, -3, and +3. Among this range, we can plot it over any data point in the world. Feature scaling is very important. Risk is minimal, right? Not like one hot encoding. Feature scaling is not a big risk at the end of the day. It's a very simple simple work that we can do, because we can scale it out. Scale it out because the range is extremely high. Again with the problem, right? Again with the problem. Now Z score in your A level Z score, the problem is we want to get the top people to the universities, or this university and that university and this course and that course and stuff. So the Z score is focused for that. So that's the problem. It's not applicable for the O levels, right? In local O levels, that's not applicable. Oh, whatever, the Cambridge or wherever that you are doing. So that's the story of this scaling. So after performing this feature scaling, we can have a common scale, a proper scale. Data is very nicely aligned to the data set. It's not having a very high skewnesses. I believe you learned the statistics, right, somewhere in your degree, unless it might be a bit of Greek, right? All of these, I'm keeping assuming that you learn z-score and stuff, you learn skewnesses and stuff, right? because those are some of basic and essentials to understand what I'm speaking, unless you are in a Greek class, right? So we have magnitudes, right? We have magnitudes dominating due to their large magnitudes, especially if you are working in a big set of outliers or some of big stories. So you should be very careful, especially when it comes to this feature scaling. I'll give a very simple again another example. Assume in my class I have 270 students, right? 270 students. Among the 270 students, 17 above 90, then 200 is below the 90. Now what I'm going to do is I'm going to divide further. I'm taking the people 50 to 90, 50 to 90, and 90 to 100. Now 90 I have here, right? 50. Below the 50, I have 110 students. So 90 students here. Now I have to scale it properly. Now you can see the classes or the bins that I divided is different. 0 to 50, the range is 50. 50 to 90, the range is 40. 90 to 100, range is 10. Correct? What I'm doing is 100 minus 90, so I have range of 10. 90 to 100, we have only 10. 50 to 90, we have 40. 0 to 50, I have something here. Now the classes are different. The class sizes are different, right? Here it's 50, here it's 40, here it's 10. So you should scale properly this kind of a scenario. General things that we are facing in our data science world, real world scenarios, right? So you should be very careful that when we are doing this kind of a scenario, unless it might be a big problem at the end of the day, right? So feature scaling is not, it's not like creating much problems, but you should be very vigilant and wise whether I'm going to apply this tactic or not, or do we have another much optimized tactic for this. So it depends on the question again. That's the point that you should understand. Next, binning. Grouping numerical data into bins can sometimes capture patterns and not evident to treating some same as continuous variables. This can be useful for reducing noise and handling outliers. Now, binning means grouping these numerical data into bins. For an example, like the same story, continue the same stuff. I have been into different class sizes here, 10, 40, 50. But if I, now in this case I have been, due to some reason I want to check something here, but I want to check something like the pass students and fail students. I can create two bins, less than 40, right? Your passing score is 40. So I don't know, if I'm incorrect, fix me guys, right? If you have got less than 40, then if you are less than 40, you are fail. If you are above 40, you are pass. So this is the simplest binning method. You divided it into two. Again, we have some issue in here. Here 0 to 40, here 40 to 100. That means 60. 40, 60 differentiation we have. If we have perfect binning, it's 50-50. Below 50, above 50. Another perfect 15, 25, 50, 75. Right? So perfect bins we have 25%, 50%, 75%, 100%. The class sizes are exactly same, equal, but the distributions might be different. Don't get upset with that. For an example, the data distribution is different. For an example, think this is again marks, right? Again, this is marks. Above 75, we have only one student. 50 to 75, we have 50 students. Right? 25 to 50, we have 30 students. 0 to 25, we have 10 students. The data distribution is different. What I'm speaking, right? What I'm speaking, the data distribution is different. Don't get upset with that. So you can create an histogram. You can create a histogram. You can see the distributions easily, how it distributed over in a equal or even binning, right? Even binning. I have created four classes in this case, right? I have created 4 bins. It's a nice work, but binning type is very important. right? Binning type is very important. How you are going to bin, whether you are going for a equal binning or not. What kind of aspects that fit for your case, what kind of scenarios fit for your problem. Again and again, I'm telling you, problem, right? The problem that you face is the problem that changing your life. So you should think how to solve this problem. So solution, it's up to you. It's up to your skills, knowledge, and attitude, and all of these things. Then you can come up with whatever XYZ facts. Then you can do whatever you want. Right. We'll go for a bit more. I believe you can manageable, right? Um, there are a lot of techniques under feature engineering context. You could learn more dimension reduction, interaction features, and blah 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 things. Dimension reduction. Now, what happens in this dimension reduction? This is the process of reducing the number of features, right? To keep most relevant information for us. We have collected thousand data, and we have collected 500 features for that thousand data, right? We have collected feature 1, feature 2, feature 3, 4, 5, 6, 7, 8, n number of features. In this case, 100 features we have, but we don't want these all 100 features, right? Assume now you are coming for an examination. What I'm doing is I'm collecting the data, that number of hours you spend, number of hours that you use for the questions, the number of lectures that you attended, and all of this data. And I'm in the examination of your cat toe, whatever the examination day, and I'm collecting the best color that you are wearing, whether it's a red color or a white color or something color. Right? Sometimes that color might has no impact, zero impact for your marks. So what we can do is we can delete that dressing color, or the vehicle that you travel, right? From house home to your examination location. How you travel? I'm collecting that data. You are travel through a bike, you travel through a van, whatever, yeah, whatever. You use any medium, right? And there's no impact for the marks, how you travel. Though you travel by bus or a train, there's no impact for that marks. So we can reduce that, right? So those kind of features are very common. But once the data collection stage comes, what we are doing, we are collecting as much as data, as much as data, as much as data. I will give a real world research related to this boxing. There are two colors in boxing players, white and red. Research has found the people who are wearing red is getting much probability of winning than the people who are wearing blue, right? So it's not a feature that we can delete. Sometimes if you are wearing red color for the examinations, you are getting much marks than the others. I don't know. I haven't done a research, but there might be. So we can't reduce it. We can't delete that feature. What I'm emphasizing is to get a decision whether we are going for a dimension reduction or we are deleting that feature or not depends on the problem, depends on the existing features, depends on the correlations of the existing features, depends on many factors. So you don't delete. My suggestion is please don't delete or go for a reductions without any reason. You analyze, you initially keep an assumption or go for a hypothesis testing. Initially, you assume there is a value for this feature too. Then analyze it, do whatever things. Then finally, you can go for an null hypothesis and whatever things you learn, right? Instance. Then you can tell, according to these analysis, there's no relationship in between this feature and the final product. So I'm going to delete. Though we have all these things, in technically, once it comes to real world problems, you should be very careful, especially what I'm emphasizing, your final examination or the CAT examination or PMA or whatever you have. It might be a set of codes and a set of data might be there thrown for your head. There might be 25 columns. Among that 25 columns, 20 columns you can delete because those are not important at all. But you can't simply delete it, right? But you can simply delete it. This column is not required at all. Say, so I assume there's no value. No, you can't. You have to come up with a proper technical discussion, critically evaluate, then you can tell, yes, of course, here you go. You can't, right? There's no value at all, then I'm going to. High dimensions means we have large set of data, lot of data. Then we can develop very powerful product. I'm not sure, I can't extract it, remember. To develop ChatGPT, if I'm not mistaken, 120 plus features they have used. Assume you are developing a face recognition system or a voice recognition system. You need large set of data set. Unless your project is scoped down to many things. For an example, if you are if you are developing a face recognition system, then you need eye color, face shape, and all of these things. So all of these are very complicated, right? Finding the features, large set of features, thousands of features, right? So you should be very careful, and you should see the insights before you analyze all of these things. It's extremely important. It's extremely powerful, right? So that's the story in here. But as we discuss some of techniques, we have to understand PCA, ICA, SVDs, LDAs, and distribution over these neighbor embedding. I'll quickly go through with these things also. So you can spend a bit of time and do some practicals and see actually. Learning theory is insufficient, guys. Learning theory is important. Yes, of course, no arguments at all. You should learn the theory first of all very well. Theoretical background should be there in your head. Number two, you should apply and see, get the experience, right? Get the experience. What is this PCA? I can remember some mushroom classification or something in the Kaggle somewhere I found for PCA and ICA. You can go to Kaggle probably. Then you can find many things, or else go for many workshops. Nowadays we have, learn, experience, get the experience, get hands on, see what happens in the real world scenario. We'll quickly go through this PC or the principal component analysis. What we are going to do is this is one of most popular method for the dimensional reduction. The transforming the features into new groups of special components called principal components, and these are new things made by adding up the first things in the certain way somewhere statistically how these things are distributed. It maximizes the variance of the data along the principal components, effectively capturing the most important information of the data. So if we have 25, 25 features, after PCA, sometimes we have only 5 features. It creates a statistical distribution among the features and see what features are highly related to the other, highly connected to the other. So the simplest method that already you know is you can create a heat map, right? You can find the distributions over in different places, then you can find how these things are going on here and there. How PCA works? We should go a bit of theories in here. Practically, you don't want us to see inside all of these things, but theoretically, you should understand to get a clear understanding. Data standardization before performing PCA, it's a common practice to standardize the data by subtracting mean and the dividing the standard deviation of each variable. This step ensures all variables are on the same scale. So a scaling method, probably these things you don't want to do manually, right? If you use a package, then that package is having all of these supportive things. So you can go through and you can apply. Then convergence metrics, you can go for operations based on the convergence metrics of the standardization data, right? This captures the relationships in between in different kinds of variables. We have different kinds of variables, and these variables have different kinds of connectivities or connections. So what we are going to do is we are going to find these things, right? We are going to find these things, how these things are connected with one the other one, right? So that's another valuable or the crucial point that to understand. Then eigenvalue decomposition. Eigenvalues are some mathematical values, guys. Sometimes you haven't worked with these eigenvectors and eigenvalues. So give a try and see what are these eigenvalues and stuff. Actually, you don't want to consider like think a lot once it comes to a practical scenario, because you in built algorithms we have all of these things included, so you don't want to bother a lot. But if you are planning to experiment something in detail, I'm pretty sure you want, it's a must to have these eigenvalues and stuff to be very clear and detailed over these places. Then choosing components, typically you will want to select a subset of principal components that capture most of the variances in the data. This subset can be determined based on the cumulative explained variance or by setting threshold for eigenvalues. Once you choose these eigenvalues, once you decompose, then you can go for this eigenvalue based thresholds can be defined. Then you can fit it. Finally, we are performing a projection. The original data projected into a specific principal components. Then you can find the reduced features. I believe it's a bit hard to understand all of these things because of these technical terms and stuff. Don't worry, give a try in a free time. See what are what are these things means. But still, if you are unable to all of these things, but you can practically do all of these things, I'm pretty sure your very first objective is done. Then you learn, now you learn some of theories, then practically see, then you can learn the theory in detail, what is this means, right? But the case is, students, we can't see specifically what is this happening, how this eigen decomposition is going on and stuff, right? It's like going inside a body and see all of these things. We are treating and going inside the body is different. So it's two different aspects. So you should clear and get a clear understand how to handle and tackle all of these things. Right. Don't get upset if you are unable to understand. Give a try later on and see how the things are going on. Another algorithm is independent component analysis, so ICA. Again, it's a statistical technique that used to separate multivariant signal into additive independent components. Now, principal component analysis is mainly focused on uh, identifying the key factors by using these variances and identifying the maximum variances to capture the correlations in between these variables. Similar, like for an example, you can take the highest correlations, PSN correlations, then you can come up with and see the variances are, how is it now. This case, ICA is focused on finding components that statically independent of each other. Simply what we are going to do is the other way around. Right? PCA focus on combining all of these correlations and finding their relationships in between here and there. ICA focus on finding components that statically independent from each other. So these are two aspects. But you know the story, guys. You can apply to a same data set and get nice outputs among these techniques, right? These are like same rope, but this rope do have two edges, two corners. You can take one corner, the other corner, one edge to the other edge, then you can play with it. So that's an interesting story. But be careful, right? But be careful. right? Whenever you are applying these things. This is useful when observed data assumed to be linear mixture of independent sources such as blind source separation problems. Now you can find it's an independently collected data over different places. Now you combine their data. Now the features do not have much principal components to be found. Instead, we have independent components find. For an example, this example is not the perfect example that I have given. Up to now, I have given very good examples to understand the story, but this case, I can't give a very good example. This is something to understand only, right? Clear? Now, for an example, assume now we are in a very like we are in an oven right nowadays, very heated environment, so everything is grasses are gone to brown and everything is going very bad. Now what we are going to do is we are collecting independently data among different locations over the country. One from Jaffna, one from Anuradhapura, one from Kandy, one from Nuwara, one from Kalutara, one from Panadura, one from Matara, one from Khatragam, one from Badula, and so on and so forth. Now the sources that we extracted is different, guys, right? We have same what we call Intel. We have a device, specific device, and that device generates the data for us. We have like Colombo, we have the main center. That device generates data for us and sharing with us, right? But what is the biggest point, guys, in this case? We assume that device is extract same. That means though we have 25 or 50 devices around the world, around Sri Lanka, we keep assumption all 30 generates extract same. There's no issues at all, but there could be some issues, right? Some mechanical issues might be there, or some data transformation issues might be there, but we assume. And in the other hand, we assume no, not assumption, we are collecting data independently. We collect data independently from Jaffna to Anuradhapura to Nuwara to Katragama to Panadura. Independent data extraction happens. So we combine the data and we are telling here, this is the data. But we haven't considered the wind flow, the naturality, or the nature, or altitude, longitudes, and all of these blah, 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 blah things. So whenever you are applying this ICA, this is the point that you should understand. We identified the data independent, right? We find independent sources and we collect the data. So the observations are independent, not from the same method. I don't know whether this example makes sense or not. Give a try to understand a bit more later on in your free time. In this context, the data reduction and ICA can be applied to decompose the original data into independent components, potentially revealing the hidden factors of sources underlying the observed data. Now, something we can't find, so this ICA would support us to find where we can apply the data. We have further couple of things, singular decomposition, value decomposition or SVD, what we are telling. Here it's matrix factorization technique, and we have three matrices in this case. In this context of dimensional reduction, SVD is used to decompose the data matrix into its constituent components, allowing for the section of subset of components that capture most of the variance in the data. Now you can realize, right? Variance plays a big role at the end of the day in data science, right? Because PCA uses variances, SVD uses variances. So variance is very important at the end of the day. Somehow you should understand how it works. Then LDA, linear discriminant analysis. It's a supervised dimensional reduction technique, considers class labels when projecting the data into a low-dimensional space. It's a must. It aims to maximize the separability between different classes while reducing the dimensionality of the feature space. It's a must, right? So it's a Very important story to understand. So we have to take LDA to see how these things are distributed into a lower dimension. Another technique we are telling is TS, right? Under this TS, what we are doing is non-linear dimensional reduction, right? It's usually highly supportive for the high dimensional data into to low dimensional space, right? We have very high dimensional data once it comes to 3D data, because we have Z factor too, right? XYZ, all of these things. So it's very complicated at the end of the day. So you should be very careful to understand how to tackle this TS. It aims to preserve local structure of the data, meaning similar data points in the high dimensional space remaining choose to each other in low dimensional space. Right. I have gone through some of the techniques, but keep in mind whether I'm going to handle with these features a lot or not. It depends on the problem. Be careful, be vigilant, wise, and mindful when you are doing this kind of work. Any questions, guys? No questions, right? Then we'll go to the last topic for today, model selection. Now you learned models last day school 3, so you can understand some of interesting aspects, and I believe you spend a couple of hours for each and every algorithm. Further algorithms will be discussed in future. So now we are going to discuss the model selection. Model selection is focused on choosing the appropriate algorithm or model architecture for your problem, because we have many algorithms most probably to solve the same problem. We can't simply tell this is the most appropriate algorithm for this case, right? We have to experiment it, right? We have to experiment it. We have lot of data, we have lot of different kinds of aspects. Now you have some understanding some of issues, right? So similar algorithms to solve your same problem. So what you need to do is you need to apply all of these algorithms and see what is the best performing algorithm for this case. To select most well or most suited algorithm, very simplest approach is, if you have a classification problem, you can take classification problem related to algorithms, then apply it. That's the most simplest method that we can do in our work, right? So we can simply go and see all of these things, then we can quickly apply all of these things. That's all, the game over, done. But there are some scientific approaches to solve the same problem, right? Now you could go through these scientific approaches, then you can save your time, experiment a bit more, then you can come up with the nice story. Now, some of common challenges in this model selection, we have multiple models, right? When we are dealing with predictive modeling, we have large collection of candidate models or models that we can use. So these models varies from different kinds of aspects. Some of the things that they assume initially, the data is in a standard bell curve distribution, or else multiple that some one model might assume we have this much of features, or the feature space is this much, right? So lot of things might be there at the end of the day to find. So these, all of these are challenges. Multiple models we have. If we have only one and only model, then that's it, game over. This is the model, we applied it, this is the output, that's all. But the story is different. But the story is different. Once it comes to a discussion that related to our, there might be many models that fit for a given scenario. And we have trade-offs. Now, each model has its own trade-offs, right? So some complex models may provide very accurate descriptions. Reality is it's like due to numerous parameters. Solving the optimization problem associations such as models with the computationally intractable. So a lot of things that you have things with these trade-offs. Simplicity versus accuracy. It's again big challenge. You have a very simple solution, a very simple algorithm. And what you are going to do is you are going to apply it, and then you are getting an output, problem solved. And in the other hand, you have very complicated in the sense, large number of features, lot of algorithms inside that, lot of processing and go on, and finally it gives some output. It depends. I can't tell. The simpler algorithm is not doing perfectly. I'll give an example. Uh, I went in here in Open University, couple of what we call presentations last week, right? Guys, they have uh, you have some of students do have what we call data. The data set, the entire data set consists of 100 data, 200 data, 300 data. And what they are going to do is they are going to apply for a neural network. Please don't tell, guys. It's really annoying for me. Right? If I'm in the board, it's really annoying for me. Why? It's like you are cutting a bread using an axe. Right? You should use the appropriate tool. You have a loaf of bread. You should not use an axe to cut a loaf of bread, right? Clear. So you are using neural network for 200 data. Even I don't believe it's fit for machine learning algorithms. You can go for a simple statistical analysis and tell whatever things. Why we want this AI? Why we want neural networks? We have large number of varieties of data, thousands of millions of data we have. Unless statistics is more than enough for a sample of data to tell whatever thing, statistics is very strong. Please don't, guys, right? It's a big challenge for me actually. If you don't have at least 50,000, at least 10,000 data, don't go for a neural network. It's like the same example. Keep in your mind, tell to your colleagues, to your seniors or whoever that I told this kind of story. You can't use, guys, overfitting happening definitely. No arguments at all. Definitely it's overfitting. A proof, right? It's proved, right? Even if you want to prove, come and I'll show you. I can prove it. If you have very low set of data and you are trying to use neural network, it's inappropriate. You should use a knife for that, not an axe. Right? Neural networks like axes, right? It's a big thing. If you have a big, like very strong tree, yes, of course, it's grown well. It's very rough and all of these things there is. Then you have to use an axe. Yes, of course. Agreed. But to cut a bread, you should use a knife, right? We have a tool for that. We have to use appropriate tool. That's the challenge of this model selection. I believe you got it. Regardless of any other theories, practical, general, common sense should apply, guys. Why I am applying? Not for the fancy story. Right? We don't want to tell, I do LSTM. Right? I don't want, from my perspective, I don't want. If you apply LSTM into the proper place, LSTM is a nice, strong algorithm, right? If you apply LSTM to the most appropriate instance, that's the output, that's the value. Even YouTubers I found, I have 100 data, then I'm applying. Yes, that's good for some demonstration purpose sometimes. They might be giving some demonstration for that case, yes, of course. But a real world scenario, a real world instance, it's a big problem. Some of the people are coming graph learning and telling I'm using this graph neural network. Then I'm asking my question is, my very first question is, what is your size of data? I have 80, sir. Then I'm telling, don't, no point at all. You can't, right? Guaranteed, guys, guaranteed students, guaranteed app. Then please don't do that, right? Challenge of this model selection is number one, question. Number two, set of data. You should think what is the problem that you are going to solve. Number two, the size of the data. If you don't have sufficient data, don't go for strong algorithms. No point at all. It's fake because it's overfitted. It's generate something, right? It's not a big deal nowadays to train neural network. Right? It's not a big deal nowadays because we have all ChatGPT and stuff. We can ask the question, generate LSTM for us. It generates. You let the data set, feed it, then it generates. That's all. So nowadays the problem is different. Right, right. We'll go for some of the things related to the discussion, like the some of techniques. We have probabilistic methods and resampling methods. These are basically best that in a scenario we have statistical involving a lot, right? Statistics involving a lot. If not, again, my general suggestion is you have to think what is the problem you have. It might be a classification problem. Then find the most appropriate classification algorithms for your case. Check what are the assumptions that they have chosen to discuss that scenario. Then what kind of resampling methods that they have done and so on and so forth. So it's a must to understand all of these things. It's a must to get a clear overview and understanding how these things are going on here and there. Right? Some of probabilistic methods providing analytical techniques for scoring methods, considering both their performance on the training dataset and their inherited complexity. These methods are guiding decision makers in selecting models that strike right balance between accuracy and the simplicity. Now we got to know a problem or a common aspect that we have to work with these scenarios, accuracy and the simplicity. Right? As I told you, I can't tell the most simplest is the worst. There might be simplest algorithm, but it worked well for the problem and the data set. Some of probabilistic model selection methods, AIC, MLTs, and SRMs. I'm not discussing these algorithms or the selection methods in detail. You have to go through and find and research and go through a bit of. But I'm planning to add some of the details in your sections or the course book. Then you can go through. But guys, I'm always telling, if you want to learn nowadays, there are thousands of millions of resources, free resources. You don't want to spend even a cent to learn, right? One common issue that I heard come across in this case is you are spending money for what we call this Udemy courses and stuff. It's fake, guys, again, right? Believe me, Udemy courses are fake, right? No point at all. Please don't spend money for those things. They are giving nice, fancy discounts, right? But you can't learn. It's similar to the YouTube tutorials that you are learning from YouTube. So my suggestion is go to YouTube and learn. That's one of the easiest method. There are a lot of resources. If you search AIC, you can go to and you can find it easier. Just search in ChatGPT, you can get thousands of examples with all of these codes even. Right. Uh, some resampling methods. These techniques help us to understand how well model generalize to unseen data, out of sample data. And some of methods are cross-validation, random sampling, bootstrapping. Right? Cross-validation means we have data, and what we have to do is we have to take the data set, partition into two or more, usually two. Then one data is unseen. We are not feeding to the development or the training of this data set. Then after model development, we use it for validate whether this algorithm is working perfectly or not. That's cross validation. Random sampling means we are taking combinations of hyperparameters for each model and evaluating their performance. So we are checking these things, and we are finding what kind of thing is going on here and there, right? Now, one further experience method is grid search. It's again a simplest method for subset for the hyperparameters for each model to find combination that yields the best performance. So this method also a nice implementation that we can do use in our work for our day-to-day machine learning algorithms development. Right, that's all that I want to give to you today. Any questions, students? Meanwhile, I'll share that day two video. Give me a second. If you have any questions, you can use chat and ask any questions. Yes, guys, what are the questions that you have to discuss? It might be a bit complicated for some students, yes, of course, right? But give a try. I have shared the link with you guys in this date school 2, and I will share today's slides also with you. Then till you are getting all the things from the course page, you can go through and see. I have shared the slide deck with you, so you can. It's in the chat. You can check that one also. You can go through and see that. Anything else you want? Any questions? Any important points that you need to find and discuss? No questions? All good? All right, then. If you don't have any questions, I'm going to stop the lecture for today. So we'll meet in days school 4. Most probably, once it comes to days school 4, everything is settled down, right? There is a question, do we need to study all classification techniques for exam? Uh, all techniques, all the classification techniques probably we can't learn in the world, but most essentials you should, yes, of course, you should learn the most essentials. Most probably, we can scope down that in our sections, uh, the essential classification problems and techniques for the examination. For the examination, yes, of course, you can scope down but my suggestion is, once it comes to real world scenario, once it comes to your job environment, if you are planning to be a data scientist, there's no scope at all. Right? I'm telling for every undergraduate, if this is your job, there's no scope at all. It's unlimited. So you need to research, find, learn forever. You can't stop until that's all, the game over. So it's a big story at the end of the day, right? For, yes, of course, for examinations we can scope, we can tell these kind of algorithms are essential. But if you are planning to do a job, definitely go out of these boundaries unless you are a normal student, so they don't hire you, right? If you are outstanding student, definitely they will hire you. That's the difference in these cases. Right, guys. I believe I have answered it in a satisfactory. Any other questions, guys? No questions then. All right, that's all for today. Then we'll meet with our day school 4. Bye bye. Till then, good luck.